All right, welcome to the 4-3 video. Our goal with this video is to use the change of base formula to calculate logarithms. Whoa, it's been a rough morning. Okay, so we're going to use the change of base formula to calculate logarithms. All right, so just to make sure that we're all on the same page, I just want to make sure that we really hammer home this idea, right? Here's the definition of a logarithm, right? If a raised to the x power equals b, then log base a of b is x, right? So that is the change of base, excuse me, not the change of base. Excuse me, that's not the change of base formula, Mr. Stevens. No, this is the definition of a logarithm, right? So here's the definition. This is the definition of logs. Now, I'm going to go back to the beginning here. And if you pay close attention, I'm going to spoil what we're going to do in 4-4 or 4-5, right? So here I'm going to take a to the x equals b. And I'm going to take the log base 10 of both sides. Okay, so here I'm going to say log base 10. I'm not going to write it. It's not there, but it's understood to be base 10. So on the left side, it's a raised to the x power, and that's going to equal log base 10 of b. And then what I'm going to do, since I don't have my notes, but you remember the exponential law of logarithms, or the exponential property, says if I have a variable here, the variable comes out front, right? So that x is going to come out front and be a multiplier times the log base 10 of a, and that whole thing again is equal to the log of b. And now if I divide both sides by log base 10 of a, so I divide both sides by log of a, then I'm left with x on this side. X then is going to be equal to, x is going to be equal to log of b divided by log of a. And that's log base 10 of b divided by log base 10 of a. And that's x. X is equal to that. Let's go back over here. And the definition of logarithms, x is equal to log base a of b. So if you remember, I think it's called the transitive property, right? It says if a equals b and b equals c, then a must equal c, right? If a equals b, b equals c, then a equals c, right? This is one of those basic understandings of logic and the matter of equations. Well, if this equals x and x equals this, then we must surmise that, so then we can draw this big huge conclusion, right? We get conclusion that, all right, if all this equals x and x equals all this, I'm going to take the x out. And I'm going to say that log base a of b is equal to log base 10 of b divided by log base 10 of a. And this is the change of base formula. It's this guy right here. And the reason why we have to use the change of base formula, let me get my handy dandy calculator out here. Seriously, do I always grab the broken one every time? Good grief. Let's see. My batteries are low. Well, it's because it's December. But third tries the charm? All right. Okay. We take a look at our calculator here. The calculator has exactly two buttons. It has the log base 10, which is the log, L-O-G, and it has the natural log, that ln, which is log base e, if you recall from the first video. So we have log base 10 and log base e. Now that's all we get. That's all we get. So if we go back to this step here, and I don't want you don't have to memorize how to do this, and you're not going to do this all the time. This is just me showing you where it comes from. But technically it's called a derivation. But if we take a look here, if I had chosen to take the natural log of both sides, then we could also conclude that log base a of b is equal to the natural log of b divided by the natural log of a. And that's very important to know. So I only have log base 10 and log base e on my calculator.
If there's any first-hour teachers willing to cover a class, please call me at 7114. Any first-hour teachers willing to cover a class, please call me at 7114.
So let's take a look at some examples of how we're going to deal with this. Thank you for the break there, Brandy. All right, so the type of questions we're going to have to deal with are very simple. It's going to say something like, round to the nearest thousands, right? Thousands. And that's 3 decimal places, right? Okay. So the example we're going to get something like log base 7 of 14. Now, I know from the change of base formula, the change of base formula says, we take a look, the change of base, Stevens, log base a of b. So log base a of b is log of b divided by log of a. All right, so log of b divided by log of a. So here, I know that log base 7 of 14 is going to turn into log base 10 of 14 divided by log base 10 of 7. And then I go to my calculator, and I get the log, and notice how it has those parentheses, so I'm going to plug a 14 in and then close it, divided by log, and then I'm going to put my 7. So log of 14 divided by log of 7. I guess, can you see that? Yeah. And then I hit enter, and I get 1.35620, rounding to the nearest 3 decimal places. I end up with 1.356. Now, I'm going to take this exact same example, so log base 7 of 14, and as I was saying earlier, I could switch and use the natural log here. Because I have a natural log button on my calculator, I want to see, does it work? So I say the natural log of 14 divided by the natural log of 7. I don't know why I use parentheses here versus there. It is just a habit. So then I say, what does that equal? And I get in my calculator, I do the natural log this time of 14, and I close my parentheses, divided by the natural log of 7, and then I close my parentheses. And now when I hit enter, whoa, I get the exact same thing. This, to me, is super cool. So I get the exact same thing, which tells me one thing very loud and clear. Whenever I have a number, my base is a number, and my argument is a number, I can always find out the value of it, and I can choose either log base 10 or the natural log, which is log base e. Let's do a few more examples. All right, let's try log base 9 of, let's go 43, right? So the base here is 9, and my argument is 43. So here, in my calculator, I'm going to do log base 10 of 43 divided by log base 10 of 9. And plug it in my calculator, I go log base 10 of 43 divided by log base 10 of 9, and we get 1.712. I got 1.712. All right, let's try another one here. This one is really funny. This to me is hilarious. So if we're dealing with change of base, I want to calculate to the nearest 10,000 or the nearest thousandth, right? 3 decimal places. When we get an example that says log of 912. All right, what's the base? All right, the base is 10. So I get a lot of students that go, oh, okay, well, that's log of 912 divided by log of 10, right? And we'll go on your calculator and we'll do this. All right, we get log of 912 divided by log of 10, and we get 2.96, right? So we get 2.96. 0. All right, I had to go to 3 decimal places, sorry. Now, this is log base 10, right? Log base 10 of 912. Well, I already have a log base 10 button. So I could have made life really easy on myself by just putting it in as log base 10 of 912 and hitting enter. Right, so your understanding of logarithms is really, really, really abundantly clear to me at the moment I see somebody do this. This is doing too much. Doing too much. Hashtag, that's extra, Mr. Stevens.